everyone. This is Budan Maheros from Data Community United for Ukraine, and we are testing our sound as usual. So we'll be back in 30 seconds like that. If you can hear us, just let us know in the chat.
So sound test, continuing the sound that you were starting. If you are watching on YouTube, it takes 30 seconds. If you are watching on LinkedIn, it takes 20 seconds. So we tested this. So make sure that you hear some of our voices. And Marcin will have an amazing session today. And we're just filling time with some blah, blah, blah.
Yeah, looks like the sound is working. I can hear us, so we are already online. Hello, everyone, again. You can watch us in YouTube, which is expected, and you can also watch us in Facebook, LinkedIn, Twitter. It depends where you are. So anyway, we hope that the best quality is in YouTube, so you can switch to YouTube, where you can push the notify me button. Anyway, we are starting. So hello everyone again. I am Budan Maheros, and this is Data Community United for Ukraine. Thank you for coming today. Today we have our fourth session, week number 2 of the conference marathon, taking 3 weeks, 9 amazing speakers all over the world, and we are talking about different technical things like business intelligence, Power BI, clouds, data science, and a lot of other interesting things, and not only technical things. So what we are doing, we are fundraising, we are collecting funds for our Ukrainian Marines. The Marines who are working in the in very hot places in Ukraine, and the copter Matrix M300 RTK, which costs about $14,500, is our goal. And so you know that copters are the eyes of our military, and they need a lot of equipment. So this is our goal for that conference marathon. So even your minimal donation is a large investment for our defenders who need to stay at the front line and have to come back alive when the war is over. So as I said, the conference takes 3 weeks, and during that time you can subscribe to our channel not to miss any of our events. You can also press subscribe not to miss anything here. And so let's start our session. So today we have Marcin Szeliga, and before going to Marcin, let me introduce our guests today. So as usual, we have Andrea Melancia. Hello, Andrea. And we also have Jenny Beccari. So she's the first day with us today. So Jenny, I guess your turn. So you can tell us a few words, and we can take not even a minute or 2 or 3. So welcome.
Thank you. Hello everyone. Thank you for the invitation. I'm really happy to be here. I have the role of data science audience marketing manager in Azure AI as part of the Central Eastern Europe team in Microsoft. My focus is communities, connections, and engagement. And I truly believe that the power of the community is strong. It's really important to be well connected and be able to spread the word around communities about the recent advancements and the services of AI. Our products and services have constant updates that need to be communicated, and more people be up to date with the most recent changes. and all the capabilities our solutions have. And I really hope that many people will be motivated from this event and it will make a difference. So that's all from my side. Thank you for the invitation. Best of luck for your goal. I'm looking forward to the session.
Yeah, Andrea, a few words, or you are as usual monitoring our streaming?
So just very happy to be here once again. Thank you all for watching these sessions. Feel free to contribute. This is actually very important. I also have an important visitor here as well. So don't forget the usual cats and dogs that we have at home. So they're also very important as well. Catalina is missing because he is actually with the dog in the vet, or himself in the vet, I'm not sure. But hopefully Catalina will join us as well, maybe towards the end of Marcin's session. So anyway, Marcin, hopefully your session, I know it's going to be amazing. So let's have a look. This will be fun. Thank you all very much for being here, and please contribute.
Thank you.
Today we have Marcin Szeliga. So I guess you could watch Marcin sessions at Power BI on air, or maybe you had a chance to watch him at SQL Saturday in Lviv or Kyiv. So he's a Microsoft MVP, a machine learning practitioner, and he is an independent consultant solving customer data related problems. He is Microsoft MVP. He is one of 2 Polish AI MVPs. He's speaker at many European conferences, such as our Machine Learning Prague, Data Science Summit, SQL Day for Developers, SQL Nexus, SQL Saturday, Microsoft Technology Summit. So he is a university teacher and author of different books and articles about Microsoft Data Platform, including some bestsellers like Data Science and Machine Learning. So it's a Polish IT book of the year 2018, right? And Practical Machine Learning. And today we are talking about AutoML in computer vision. So Marcin, your turn.
Thank you. Thank you very much, Bogdan, for having me. Yeah, hopefully you can see my screen. You should see the title, Medical Image Analysis using AutoML on Azure. Of course, if that's the case, great. I was already introduced, so instead of repeating you, Bogdan, let me just thank you again for the invitation. It's really important for me, a special event. I'm from Poland, I'm Polish. And as you may know, it was almost exactly 83 years ago when the Soviet Union invaded Poland without declaring war. And it took 50 years till the Soviet Union collapsed and the last Russian soldier left my country. But finally it happened. And will happen again, only this time much faster. So instead of introducing myself, let's change the topic to technical agenda and deliver the session. I will start with talking about challenge. By the way, I know it's a remote session, obviously, but still maybe we can make it interactive as possible, okay? So don't bother about the delay. I know that you may feel uncomfortable because it takes like 30 seconds till I get your question back, but feel free to ask as many questions as you want. And I already asked Andy and Bogdan to let me know if there are some questions, and I will try to answer them either immediately or at the end of the session, because Bogdan said that if needed, we can prolong the session a bit. So stay interactive. That's the point. And we will start with some challenges in those kind of computer vision or machine learning projects in general. Then briefly, I will introduce you to the environment that I'm going to use. Basically, Azure Machine Learning Service. And then two techniques used during those projects, because as you will see, I actually use the environment that I'm going to show you during two projects. So the first technique is transfer learning, and the second AutoML. Maybe you are familiar with those techniques, maybe not. To be sure that we are on the same page, that will be a quick intro. But the main majority of the session will be dedicated to show you just three computer vision tasks. The first is image classification, then object detection, and finally instance segmentation. All using medical images, of course. So challenges. As a member of board for Polish Association Artificial Intelligence in Medicine, the goal of this association is to show the value of AI or machine learning in medicine by solving real problems. That the association was established a year ago, more also by my colleague, a doctor, so medical practitioner, and he asked me if I can help you with this problem. So there are X-ray images visible here, and on this one, the bone, very small bone, is broken. The point is that sometimes the broken bone is not visible on those X-rays. So as a general procedure, if you're a patient, you will be treated as it was actually broken, and after 2 weeks, the X-ray will be repeated, because after 2 weeks, the damage is clearly visible for skilled professional. But still, it's 2 weeks, and during those 2 weeks, well, your mobility will be limited. So maybe we can build a machine learning model that will be able to see unseen, the invisible damages right away during the first X-ray. That was the goal, and the problem is well known. maybe after the session you will visit this website. So it's one of the many papers related to this problem. None of them they actually used AI or machine learning, but they tried to be, except this one, they tried to build a model or find a way to detect those damages as soon as possible. But and then, yeah, I will talk about those bullets soon. I'm starting with the very last one, business value, because in my opinion is the most important and quite often overlooked challenge in our machine learning projects. So as you can see, there is a model. If you are familiar with those metrics, or quality or performance metrics for machine learning models like recall, precision, accuracy, or area under a curve, the results looks great. Yeah, it will be nice to have this kind of model, but from the doctor perspective, so end user perspective, the model has actually almost no value. Because if you are a doctor, if you are working with this for years, you know where the bone is. So this is not that important to find you the bone on an image. And the damage in this case is clearly visible by skilled eye. So again, the model is not helping. It's not one of those problematic cases I told you at the very beginning. So what I'm saying is, you can spend any amount of resources, because all those challenges that I'm going to talk about shortly are actually quite heavy challenges. you can spend any amount of time and resources solving, well, problems, but not real problems. So the added value, the business value will be negligible if you follow this path. You should not start with data. You should not start with algorithms. You should start with talking with the end users, business users, in this case, doctors, what they actually need. And if you do this, you will see that data collection can be a real issue. Sure, there is a lot of publicly available images showing you broken bones or COVID cases, why not? But only a small fraction of those images are actually interesting for the problem that you are going to solve. And I don't know about you, you're in Poland. How to say this? It's not that easy to find the right data if you work in Polish hospital. There are computer systems, of course, but quite often you will find out that you have data from 20 years, but it's not searchable. You cannot find those cases because those codes that you were used to annotate those cases were needed, but they are not searchable. The system was designed like that. And manually reviewing all those images, all those cases 20 years back, well, a month of hard work. So data collection is a big issue. It's a challenge. And then it's quite private data. And all those regulations, including GDPR, are in place. So probably you should start this along with data collection procedure. You should get access, a legal access, a permission to process the data. It also, at least in Poland, takes months, generally speaking. But let's say that we managed to fetch the data and we are allowed to analyze the data. Now it's time to prepare the data. Basically, annotate all those cases properly and be very sure that you did it correctly. Because all those algorithms, all those techniques that we are going to talk shortly are, well, they are learning from data. Garbage in, garbage out. Sometimes even a few mislabeled cases will ruin the performance of your model. And the last bullet, the last challenge. To train a deep neural net by yourself from scratch requires a lot of compute power, GPU power, and memory. This challenge probably is the easiest to solve. It's related to money directly because we can use a public cloud like Azure. So let's talk about the environment. I told you that I use Azure Machine Learning for my projects. You have heard a bit about one of those projects. Azure Machine Learning Service, if you are not familiar with this, is actually an umbrella. So it's a set of Azure Cloud services that will provide you the environment to build end-to-end machine learning pipelines from data storage, data preparation, data quality assessment, modeling, of course, assessing the model performance to deployment. All in very flexible manner. For example, you can use any Python library that you are willing to. It's framework agnostic, and the Python SDK is getting better and better. So it's one of the most commonly upgraded or constantly upgraded Azure service, I think, but in a good way. You will see this Azure Machine Learning service shortly. So to use it, of course, you have to have an Azure subscription and probably a bunch of Azure credits as well to launch those GPU enabled compute clusters. Okay, so there is a compute power available. Still, I'm not going to train my model from scratch. That will be silly. Probably nobody is doing this. What we are doing in this deep learning area, we are using transfer learning. Deep learning are basically neural nets. Deep means that there are multiple layers. But the point is that almost all of those layers are not responsible for classification. So the goal of all those layers is not to classify an image as a cat or a dog. Instead, all those layers, probably convolutional layers, but not limited to, are needed to extract useful features, visual features from raw data, like basic shapes or more complex shapes. And if you think about this, shapes are shapes. So we can train a model based on ImageNet database or any publicly available data set, and then reuse all the knowledge, all those weights established during this training, costly. It may take months even, because the network is really deep and the number of images is relatively huge. So we can transfer all those weights to our new model. We can start from the knowledge gained previously. And there is a lot of pre-trained models available to use, as you probably know. The point is that the question is, can we actually apply a model trained on images like cat, dogs, whatever, to X-ray, to medical images, to classify a cancer, maybe, so cells. And we will see shortly that the answer is actually yes, to spoiler alert. So transfer learning means that the majority of the pre-trained model is being used and only adjusts to a new goal, to a new task. How we are doing this? We are setting during the training procedure. So the number of images can be quite low. As you will see, even 150 will be enough in some cases. So we are setting only weights for the very last layers of this huge neural nets, those layers that are responsible for classification, for assigning an example to one of possible classes. So a classifier will be trained. If you want, you can retrain also the whole network, setting very small learning ratio, but I didn't, and it worked quite fine. So it looks like we solved some of our initial problems. Not all, but we are heading in the right direction. Because the next issue is how to speed up the procedure, how to actually focus on business value. I know the modeling is very interesting, and if you're a data scientist, probably you would love to spend as many time on this phase as possible, but actually you should think about the business value, the added value, not about how great your model is. So maybe we can automate this modeling part as well. And that's why automated machine learning is so popular. It was popular years ago, first when the training data was tabular, but now we can use AutoML for computer vision, so for deep learning as well. But first, what AutoML is, to be sure that we are on the same page. So there is multiple features or input variables. In case of images, there will be just pixels, and which are important, which are not. It's not that the more input features, the better. Probably it's the opposite. You should only use the important features, not all of them. But there is more. There are multiple machine learning algorithms, and each of those algorithms can have even a dozen or more hyperparameters. And based on those hyperparameters, the overall performance of this machine learning pipeline, because you can see its pipeline. The first step is data preparation step, then is the algorithm selection step, and finally the hyperparameter tuning step. All those steps combined into machine learning pipeline, AutoML pipeline. And the overall performance of this pipeline depends heavily on all those things. So what we are doing, we are, well, basically guessing, trying multiple models, multiple combinations, and sooner or later, we'll find out the good enough model. So that's, as I said, that's the fun part of the process, but maybe it will be good to automate this step. It can be automated. And now it's finally time to show you some of those things in action. Let me do this like that. Okay, so first task will be image classification. And we are going to start with data. So what hopefully you see right now is the Microsoft Azure Machine Learning Studio. So a single portal used to prepare data, train models, and even deploy those models to production. So multiple assets, as you can see on the left side of my image. So you can work with all those assets, including computes. Okay. And compute clusters. Some of those compute clusters can be equipped with GPU accelerators. That's the point. And data can be stored in data stores, but what's more interesting is a data set. So let's have a look at this X-ray training data set, the one that you show on a slide. It's based on this COVID-19 pneumonia, normal chest, X-ray, PA data set. But what I did, I just selected 150 examples. It's not that much, 150. And I divided those examples into train and test sets or validation sets. What's important, the data set is perfectly balanced. So I have 35 cases of COVID, pneumonia, and normal X-ray chests. And as you can guess, for validation data set, there is 5 examples per class. Maybe you noticed that this data set, maybe not because it's not that obvious, that clearly visible here, but it's a tabular data. it contains the image URL and a label, not the binary data itself. So now, with this, we can start training our models, or I can quickly show you how to build this kind of data sets. This is not needed probably any longer. So yeah, there are some images like this. Great. And now you have to build this tabular data set containing the class and the link to a binary data to the image. So the image must be uploaded to Azure storage. I'm doing this right now, and then registered as a data set, the one that I showed you. So just a path and a label. And with this, we can start the modeling part. Okay. Hopefully you can see clearly the code. I found the code, the GitHub repository based on because I just adjust the code to my needs. It's a Microsoft repository. And if you remember the title of my session, medical image analysis with AutoML, so search using this phrase and you will find this, the base repo easily. But still, hopefully you can see the code clearly. So we have data, we have a compute power, this cluster, and let's prepare the experiment. And I'm going actually to copy paste the name of this experiment because it will be needed shortly. And that's it. That's the whole experiment. It's transfer learning without automated machine learning yet. So what I did is I built this AutoML image config object by specifying an image task as image classification, basically assigning the image to one of 3 possible classes. And then you have to point to the training and optionally validation data set. This hyperparameter sampling is actually, well, I'm not using this because it's a single hyperparameter. So a single base model was used here. And the number of iteration was limited to a single iteration. So we are here. We are doing the modeling. And the first question is actually, am I building this model on 135 images only? The answer is no, because data augmentation techniques will be applied automatically. And we are doing, so the first step of this AutoML pipeline, we are heading into AutoML. All those transformations will be applied, and they are not configurable, at least right now. Probably they will be shortly. I told you, the Azure machine learning is changing rapidly. So there is the random resizing and cropping, flipping, color jittering, normalization. As a result, the number of training examples is greater, is because I'm training my model on slightly modified images as well. And now there is a list of models, pre-trained models that can be used for this AutoML task. If you are a data science geek, maybe you want to remember or this slide or have a look at those URLs. All those models are well described, so the architecture and achievements, the performance of those models, the techniques used. Probably if you are going to learn how those algorithms work, how those models were built and trained, I will start with ResNet and then follow to ResNet ST, ResNet XT50, VIT, and finally mobile net, which is greatly reduced models in size, but still performing pretty good. So it looks like I can use multiple models, not a single one. So I did this. That's the second version of the same experiment. Only this time the parameter space was defined. And if you are familiar with AutoML library, any of those many available machine learning AutoML libraries, this looks familiar. You have to define the search space, and some hyperparameters are numerical, like this learning rate. So there will be randomly chosen from uniform distribution with the mean 0.001 and the standard deviation 0.01. Other parameters can be discrete, like the optimizer. So maybe the classical SGD or maybe ADEM. The batch size, well, with this one, you should be careful because too big batch size means that you have to have a more powerful cluster. Otherwise, you will see out of memory exception. And now the models and hyperparameters or parameters specific to those models. You can do this as well, maybe number of layers to freeze. If you remember the slide about transfer learning, counting from the last one, by the way, or number of epochs. So how long I'm going to train those models. So that's a parameter space. But then you have to define tuning settings. I just set the number of iteration to 10 and concurrent iteration to 2 because the cluster I showed you may scale out only up to 2 clusters, at least for me. There are some limits on the subscription level. And the sampling procedure, I'm using random sampling. So I'm basically will choose the SGD with the learning rate 0.03 and the model, this huge VTBR 6224 layers, different combinations of those hyperparameters. 10 of them will be checked. But some of those combinations will, well, to optimize the procedure, you can terminate some trainings earlier because it will be clearly visible after maybe 2 intervals, so 2 epochs, that the model will be far worse than the best one that you already trained. So I'm doing this. I'm defining this bandit policy by defining this slack factor. And if the model is worse than this threshold, the training will be stopped earlier. And that's it. Now the AutoML image config object looks very, very similar to the one I showed you. And with this, we can have a look at the results. So of course, I launched this in advance. So there should be the AutoML multi-class classification experiment. It took me 30 minutes, not that bad, to train a model. Looks like I checked, in this case, just 3 models. interesting. There are different execution of this experiment. And if I go to the child jobs, you will see, okay, now I know why, because one of the combination of those hyperparameters was not right. So let's have a look at this one. Performance metrics, as you can see. So here again, just three algorithms because the same error. Let's forget about. Let me have a look at the last time. Yeah, because it was already good enough. So just 3 candidate models, and let's have a look at the best one. What does it mean, the best? You will see shortly. And if I have a look at the metrics, I can configure this based on this precision recall chart or whatever else. Confusion matrix looks like the model was perfect. So what we did in automated way, I can be sure that I can apply those pre-trained models, model trains on images of cats and dogs, to medical images, to X-ray images, and it will work, saving me not only a lot of compute resources, it was just 30 minutes, but also giving me this very good performance. Probably, for those images, probably I will be able to train a model from scratch and also get the same performance. But for more complex problems, like the one that I showed you, the invisible broken bones, it's not the case. Okay. So I showed you all those hyperparameters that you can set. The sampling methods is random sampling and error determination policies that you will see during the next experiment. And what does it mean, the best model? For image classification, the best model is found based on accuracy. So it's confusion matrix. The accuracy is the number of correct prediction divided by the total number of predictions. So higher is better. But I'm going also to show you the object detection class task, and for that the different evaluation criteria is used. So if you are not familiar with this intersection over union metric, have a look at this picture, because I'm going to use it in the next demo. This one, by the way. So looks like we have a model. Now it's time to deploy the model and use it. And what I did, I get the best model, okay, because there were multiple child runs. The scoring script was generated for me automatically. How nice. So that's the scoring script built for me. What I have to do is to build the inference config, so the scoring script and the environment under which the script will be running. But the environment was defined for me as well. So I'm just showing you the environment. So with this, I'm ready to deploy web service. Probably you should not use container instances for production workload. For sure, the 8 gigs of memory is not that much for deep learning models, but for demo purposes, it was enough. So I did it. The service was deployed, as you can see. So now I can send a test image, so a completely different one, the local image, and I got all those probabilities. And maybe it's better to show you this visually, and that the model was right. A different image, as you can see. Okay, Yes, that's true. So that was the first class, the first task that we can solve using the AutoML combined with transfer learning, the easiest. And you have 15 minutes to go through to remaining tasks. So the first is object detection. So now I'm not going to classify, assigning the whole image to a single label, to a single class. The task is more complex. Now I would like to detect where something, an object on image is, and what this object is. If you think about this, there are two different tasks. The first is more regression-like, because I'm going to predict the bounding box coordinates, so real numbers. And the second is classification for sure, because I would like to detect it was a red or white blood cell here, or platelets. So the data, the data set, again, the tabular data set is more complex. It's not only an image URL, but also all those bounding box coordinates and labels. Okay. So as you can see, I decided to increase the number of training images to almost 300 to build this, to solve this problem. Okay, data augmentation techniques are exactly the same. Of course, there is a random crop around bounding boxes, but resizing for flipping is the same, normalization is the same. The base models are completely different. They are based on you only look once, V5, or faster RCNN, ResNets, or even the slightly modified faster RCNN ResNet for RetinaNet ResNet. But from the modeling perspective, it's very, very similar. So let's have a look at this experiment. So now we are talking about cell segmentation. And let's go directly to modeling part, because data preparation, well, it's data preparation. Still, to prepare data is a lot of work, sure. And as always, you can expect spending even 75%, more or less, the overall time of your project working with data, especially because this format, these tabular data sets are quite unique to Azure Machine Learning. But let's say that we have the data registered as a data set. So now we can use the data, looks like this, okay, the label, the bounding box. By the way, bounding box has very precise definition, is the smallest rectangular area that contains the whole object. And you have to have those bounding boxes. So data labeling is a challenge. And I just, to simplify this experiment, again, I selected just a few cancer cells types from all this huge publicly available data set. And it looks like this. Okay. Okay, so segmentation. Sorry for the. No, I will finish this part and then we'll complete with slides. Sorry for that. The segmentation, 300 images, quite large. and the batch size I had to reduce the batch size to 8. Otherwise, yeah, out of memory exception. And so that's a mask RCNN, RESTnet based model used. And the number of box per image is quite huge, multiple cells visible there. Yeah. Thank you. I know that there is also a raffle or something like that. I will try, but if you have questions again, there is enough time, as Andy mentioned, to discuss those things, so we can focus on actually what you are interested in and discuss those topics. But first, let me finish. So, what's different? Again, AutoML image config object, but the task is different. Image instance segmentation. I have to provide the compute, the training data set. I skip the validation data set, so the default validation procedure will be applied, which means that depend on the number of examples, a part of it will be randomly selected and used for validation. No cross-validation because it may be too expensive to do cross-validation for this procedure. And here I'm starting with a single iteration. Okay. And let me show you the experiment result. So again, jobs. And we are searching for segmentation. Good. So it took longer, 31 hours. But still, the performance is not that bad. You might think that this mean average precision is pretty low, but I will show you how it looks like and what this mean average precision actually means. So that's the segmentation part, the transfer learning part. Then what I did, I increased number of iteration and defined the hyperparameter search space. Maybe longer is better, or maybe not. By the way, this is interesting. So let's have a look at all those child jobs or the overall performance. Yeah, that's not the one I wanted to show you now. So again, maybe with segmentation was also the case. Or for sure it was for object detection. Oh, something like that. Some training finished earlier, but this is the whole experiment. And again, output logs or models, child jobs and trials. Yes, exactly the chart I was looking for. So clearly, those two candidate models were not good enough. And here is this hyperparameter search space defined, showed like this. You can switch from parallel coordinates to 2D or 3D chart, but probably this is the best. So different combinations yield to different performance, in this case measured by mean average precision. And those two were not good enough at this stage after 6 iterations. So the training was stopped immediately. So saving time and compute resources, maybe this training was also stopped earlier. No way that the model will be better if you wait good enough if you wait longer. Okay, so that was the task. Again, I deploy the model and then use it. So it looks like this. And now it's the chart showing you that this mean average precision was actually quite good. That's the original image. That's the ground truth. So the data, the image labeled by skilled professional, in this case, and that predicted segments. Sure, for different kind of, different type of cancer cells. So this is SKOV3, and this is A172. Both are pretty nasty. So it's not that bad. And for sure, at least for me, I can see better those cells, those cancer cells on this image than on the original image. That's the point. Okay, and again and again for different kind of cancer cells. It works more or less similar among all those classes. This is important because now, sorry, again, I'm going to finally explain what I did. So the instance segmentation task. And now you know the task was to help you see some cancer cells on X-ray images. So there's a lot of those objects there, but the point was not to detect them, not to classify them, but to mark them on the original image. That's the instance segmentation. So there is no, because probably it's not that important that that's a cancer cell and this is a cancer cell and it doesn't matter. For me, just cancer cells. So the segmentation is the right way to work with this kind of data, not detection or recognition. Again, data augmentation techniques were applied automatically, not configurable, and the single base model, mask, RCNN, ResNet, FP, and described here, and a number of hyperparameters that you can set. The only sampling methods, random sampling, early termination policy. Yeah, you can configure them. If you are interested, ask me what the difference between a, probably you can figure out what's the difference between median stopping policy and the bandit policy that I used. If the performance is below median after some trials, after some iterations, and here you can define the threshold. So in my case, 20% or worse in relation to the best model at the same stage means stop training area. But the metric is quite interesting. So that was mean average precision. And it's not the precision compute based on confusion matrix. It's the precision that you can find under precision recall curve. That's why 0.4 in 0.35 in this case was a quite good result. Because, well, under this precision recall curve, if you, what's the problem? If you change the threshold, you will get a different results. So if the threshold is pretty low, let's say like this predicted box will be a false positive. If the threshold is pretty high like this predicted box will be a true positive. So this depends on the threshold, how much those areas, the predicted box and ground truth overlap. And you can change the threshold. So by changing the threshold, you can get a different results, and you can have a mean of those different results. That's a mean average precision. And what's more, you have to calculate this mean across all those classes. to which an object can belong. So with this, we actually managed on time by my mistake, because I didn't show you one experiment, the one that I was talking about. So no cell segmentation, but object detection. So blood cell object detection. Give me a minute or two, I will be quick. So I will just point to differences. So that's the experiment name. Let's copy paste it. It will be needed shortly. And let's forget about the data preparation part. So that's the tabular data set containing the path to the images and bounding box coordinates, and of course, labels. That's the difference. The image task is image object detection. And I'm starting with just transfer learning. Let's use you only look once V5 as a base model and launch the experiment. So with this, we will see something, yeah, like that. So that's the single vanilla transfer learning, 20 minutes. And this is the AutoML added to transfer learning, 1 hour. Pretty good result if you think about this. And if you take into consideration the limited compute resources, just the single NVIDIA NC12 cloud compute cluster, and still I was able to train those models. And the mean average precision, the one that we discussed, for the best model was 93% in this case, because it's not all about segmentation and hundreds of those objects visible on like blood cells, cancer cells in the project that I showed you. But here we are just detecting those blood cells. So let's have a look at those metrics. And yeah, against for the best model, against different steps of like precision or recall, looks good. And we are happy with those results, not those, but those results. Hyperparameter definition, so search space definition, experiment definition. The best model was downloaded, and as well as scoring script and the environment needed to launch this script as a web service. So I did it again. And now the output looks like this. That's the prediction query. So I'm sending HTTPS prediction query, and I'm getting the response back. Probably it's better to visualize the response. And it looked like this. Okay. So now it's time to be interactive if you wish. If you waited till the end of my talk, now it's time, and I will use this time to wrap up. So what we found, because we are actually using this platform, this AutoML on Azure Machine Learning to work with medical images for those projects that I'm doing for Polish AI in Medicine Association. And actually, I showed the doctors some of those results after the first not so good initial stage of our first project to encourage them to keep working on data. The first data set that we got contains only 50 images, but there were like 15 classes. It was hard actually to solve this this problem. I show them those results to prove that if we get more data or better quality data, we will succeed. And it turned out that with this, it cost me not that much in terms of time to demonstrate the ability. With this, they start thinking about a new project, even more ambitious than the one that we discussed at the beginning of my talk. And the project is in progress. So the ability to automate some tasks allows you to reduce the time and cost of experiments. And with this, you will have more time and more resources to focus on business value, on value added. And this is a huge, this game-changing factor. If you do this, your chances of success will increase a lot. What I showed you also is that you can combine AutoML with knowledge transfer. So with this, the compute resources, the GPU accelerators, the number of images, the amount of RAM needed to train your models should not be issues any longer, because you will be able to train your models faster based on just a handful of examples. Again, game changer. So, any questions? Bogdan, Andre.
Yeah, question. So, can you hear me well?
Right? Yes, I can.
Yeah, great. So the question is, we all know that garbage in means garbage out. So, how do the errors, wrong data markups impact on the result? Yeah, we all know that more errors in the markups we have, the less quality data we have. So, but for example, if we are investigating bones and they are marked wrong, and we are checking whether the bone is healthy or not, and the wrong markup means wrong result. But what percentage of errors can we put here not to impact on the result? Because if you talk about what the value of the error is. So if we are talking about a retail project, so we understand that our mistake is wrong numbers. If you do a mistake in a healthcare project, the mistake could be someone's life or health. So like that.
Sure. So it's pretty important question and quite complex. There are multiple parts in this question. A great question. So first, what about the training data? Remember that due to transfer learning and this AutoML, you can greatly reduce the raw number of examples in training data set. So we are not talking about thousands any longer, but maybe hundreds, maybe just like 50, like in the first project that I showed you. So even, 5 mislabeled examples, it's already 10%, isn't it? So I would say there should be no mislabeled data in training data set at all. And you can even check this. It's mathematically proved because there are so very specific attacks on neural nets, deep neural nets. if you craft some examples in such a way that it's the distortion is invisible for humans, but detectable by a model, it's a common vector attack, well known and well documented. As I said, a lot of research papers about this. So they checked that a single crafted example means that the model will be, that you can launch this attack against a model. So looks like the number of mislabeled or wrongly labeled training data, pictures in this case, images, should be zero. And that's the goal about data preparation is important part. You have to collect, let's say, like 100 of those X-ray images or any kind of images, and then go through the very strict process of data preparation and validation. And the domain experts are needed here. I'm not able to label this data by myself at all. You have to work with domain experts and then cross-validate the work that they did, the label that they used, because they can make mistakes as well. And as we greatly reduce the number of training examples, one mislabeled, one error means 1% if the total number was 100, and 1% is not that small number, yeah. So that would be my answer. And that was the second part. Yes, the consequences of mistakes can be huge in this case. Sure, that's why just building those metrics like recall, precision, or area under curve are not enough. I showed you those because that was the good point of this talk, to show you the Azure ML with AutoML features for computer vision. But there are very technical metrics, not business-oriented or domain-specific metrics. So first of all, probably it will be good to explain why the model said cancer or no. So, and we can do this. We can explain those images. There are open source libraries and frameworks exactly for that. So explainability is the basics of, well, trust. If we are, the discussion is heading into the ethics in AI area, which is actually very important. And the basics, the base of the ethics or trustworthy AI is explainability. So probably you should add the explainability part to your projects for sure, if you are working with medical images. And the last part of my answer, sorry for long answer, will be again related to business value. Though even if you get the recall like 0.8 or precision 0.9, it still the model may be useless, faulty, because it's a technical metric. It's not directly related to business problem. Think about a better metric if you can, and evaluate the model using those more business-oriented metrics. This will help you to detect the problem that you ask for. If there were mislabeled examples in the training data set, the recall or precision still may be high, but the business metric probably will notice this problem and will be way lower.
Yeah, and thank you. And you mentioned that we have not so many annotated data, all right? So is it maybe I missed the point during managing streams? So, but is it some characteristic of the AutoML that we have like 100 examples like that for training, or this is just this particular case? Maybe you can highlight that.
Okay, so very good, very good. The point is that due to combination of transfer learning with this AutoML as is implemented in Azure Machine Learning, probably maybe in other frameworks as well, I don't know. You can just use like 135 training examples and train a very good model. Yeah. Thanks to those two facts that we are transferring the models, pre-trained model, transferring the knowledge, and then doing this pretty advanced actually and intelligent modeling. It's automated, but it doesn't mean it's actually, well, worse than our own, well, imagination. Actually, if you have a look at Kaggle.com website, there are multiple competitions and ladders, and you will find AutoML models at top of almost all those ladders because AutoML is simply pretty good approach.
In what cases can we benefit of AutoML? I mean, there is an opinion that AutoML is used for investigation or research purposes, but in production environments, when the customer needs some like real results, how can we use AutoML there?
Okay, very good. If I got your question right, the problem is that we build this model using AutoML approach, so we actually don't know what we can check about the algorithm, the data preparation part, and all those hyperparameters were set for us automatically. And soon on later in production, we will have to retrain the model. And what if the model, which was pretty good last month, now is horrible? What can I do about this? Because I'm using AutoML, so I have no control over it. If that was a question, that's a great question. And the answer for that is that not for computer vision tasks yet, but if you are working with tabular data, like, I don't know, building a classifier or regression to predict the price of market stock, whatever else, or I don't know, customer churn, yeah? So if you are using AutoML, Azure Machine Learning AutoML, for those kind of tasks, among those assets, I showed you that the scoring script and the environment definition were created for me, so I just downloaded it from the job. And for those classical tasks, the model, so the pipeline will be scripted. So you will get a Jupyter notebook with the best model, with all the procedure to train the best model without AutoML. So there will be all those feature selection steps that was found the best, the chosen machine learning algorithm will be used. So you will have this notebook, and you can use this notebook to retrain a model, and you will get for sure the same result. So I'm saying with this, you should be fine using AutoML on production. So no limits.
Yeah. So looks like we are a lot out of our time, and maybe the last question. So it's a great presentation. So if someone wants to start learning I would say start trying AutoML, and I guess there is a chance to do it in Azure, having 200 credit, right? And
yes.
So what kind of tasks can a person do having this small credit, since it's like it's AutoML, and I guess it needs a lot of resources for some challenging tasks, maybe not for very simple ones. So what can you do with this amount? Yeah.
Okay, the good question. So the question is about money. The money sooner or later is the important topic. So let's have a look. First of all, if you are using AutoML for tabular data, like, I don't know, to win the Kaggle competition, to predict the Titanic survivors or not, stuff like that, you don't have to use a GPU compute cluster for that. You can use the standard virtual machines, like the standard DS11 V2 maybe, and the price for this is 90 cents per hour. Okay, and you will spend an hour, $1 maybe to complete the AutoML run, maybe 5 if you are crazy about the hyperparameter search space. So actually this 100 Azure credits, it's enough to start. If we are talking about the computer vision, it's slightly more expensive. It will be like maybe $2.50 per hour. So if you remember the first AutoML, the object classification ran for 30 minutes, so $2. Not that bad, again, yeah. But sure, this is very good question, because that's exactly my point. My point was that there are some challenges, and one of those challenges is compute resources here. So with AutoML, transfer learning, all those stuff I showed you, it's not a big deal anymore. Yeah? So use this 100 free credits to play with AutoML, it's enough. Yes.
So let me just add, if you are a student, you can actually get some free credits for Azure as well. So, why not? Just go to azure.com/free, and then it gives you some weird address. And then to the end of the address, you say /students, and you can get that for free. So it's like $100 US per year. It's not a lot, but it's better than zero. So give it a try. It's better than zero anyway. So give it a try. It's better than nothing.
Sure.
You have to be in a educational domain, right?
Yes.
Correct.
Exactly. So sorry for taking being late. It's almost 20 past 7 p.m. in Poland, but
and 8 p.m. in Ukraine.
even worse. Sorry again. But
no, it was great, really great.
Okay, so back to you, Bogdan, and I'm stopping sharing my screen.
Yeah.
Okay.
Oh, yeah, I see Catalin coming to us.
Okay, and Ricardo is also here, so some of the previous speakers as well.
Yeah, I guess Jenny has the camera turned off. Oh, yeah.
She joins. Okay, great.
Catalin, we are waiting for you for a second. Catalin is joining audio. I guess it takes up to 10 seconds, like that. Let's wait for him to see everyone. Maybe we take a picture here. Catalin?
Catalin was at the vet. I'm not sure if it's for him or for his cat.
Yeah, that's a good question. But unfortunately, Dooley has one tooth less.
Oh.
Yeah, I can hear myself somewhere. I don't know where exactly. Let me turn off everything here. Yeah, I found myself. Yeah, we can see Catalin. Yeah, that's done. Thank you everyone for coming today. Marcin, it was a great session. It took almost 1 hour and a half to highlight all points here. Catalin, I guess Andrea is going to his cat, right?
But I will look. Sorry if I please subscribe and please click notify on YouTube. That will help.
Yes, important part.
Yeah.
Exactly.
Yeah, thank you everyone for coming today. It was a great session. We highlighted a lot of topics related to AutoML, to quality that you can reach using AutoML, the corner cases. I guess we had a chance to highlight some corner cases. And thank you everyone for supporting Ukraine. So it's dark times that we experience in Ukraine now. And don't forget that one of the purposes of the conference marathon is to collect funds for our military, for our marine units who are in hot places, and they need additional eyes. And those eyes are copters that can show them a lot of our helpful things. So we are currently at the beginning of our week 2. So we have 2 sessions tomorrow and the day after tomorrow, and we also have the week 3. The week 3 is more related to Power BI. So this week we'll be happy to hear Andrea, who'll be talking again about data science, about some basic things. And if you want to catch some basic things and approaches in AI, come tomorrow and watch us. And they will have Murilo Miranda on Thursday, and he'll be talking about our elastic pools, I guess. And it will be a great session. We'll have our one more co-host on Thursday. It's a surprise, I guess. Almost all speakers here know him, so come on Thursday and see everyone. Thank you for being with us. I hope to see everyone very soon in Ukraine free of invaders, and where people live normal lives, not like we do now, but we all believe that dark times disappear and we all live normal life. And to see all that, we need to support our military who defend everyone here in Ukraine, and not only in Ukraine, but in Europe, in all over the world, since the war started here in Ukraine. And the only one chance to stop the war at all is to stop it here, stop it in Ukraine. Thank you. Have a nice evening or day if you are not in European continent. Thank you.
Bye.
Thank you, everyone.
See you soon.
Thank you.
Thank you.
Thank you, Marcin, for an amazing session as well.
Yeah.
Bye.
Bye. Thank you.
See you tomorrow, everyone.